What if the very fabric of reality is far stranger than we've ever imagined? What if the rules of time and space, the ones we take for granted, are riddled with contradictions that even the brightest minds can't fully explain? Welcome to a journey through the mind-bending world of space-time paradoxes, where the universe's deepest mysteries challenge everything we think we know. From the mind-boggling grandfather paradox to the eerie Fermi paradox, these 25 cosmic puzzles push the boundaries of science and philosophy, leaving even the most brilliant physicists scratching their heads. In this video, we'll unravel these enigmas one by one, exploring how they reshape our understanding of time, space, and existence itself. So, buckle up, because by the end of this exploration, you might just question the very nature of reality. Let's dive in. Now, turning to the first of our 25 spacetime paradoxes, we encounter the infamous grandfather paradox. Imagine this: you build a time machine, travel back to the past, and somehow prevent your grandfather from meeting your grandmother. If they never meet, your parents are never born, and neither are you. But if you were never born, how could you have traveled back in time to stop them in the first place? This is the grandfather paradox, a classic thought experiment that highlights the logical contradictions of time travel. It challenges our understanding of causality, the idea that every effect has a cause, and raises questions about the very nature of time. Is time a fixed, unchangeable line, or can it be altered? Scientists and philosophers have debated this for decades, with some suggesting that the universe might prevent such paradoxes through mechanisms like parallel timelines or self-correcting events. Popular culture has also explored this paradox in movies like Back to the Future and Looper, where characters grapple with the consequences of altering the past. The grandfather paradox isn't just a fun mental exercise. It forces us to confront the limits of our understanding and the strange possibilities that might lie within the fabric of spacetime. As we move forward, this paradox sets the stage for even more mind-bending questions about the universe and our place within it. Now, turning to the second of our 25 spacetime paradoxes, we delve into the intriguing Bootstrap Paradox. Picture this: a time traveler goes back in time and hands William Shakespeare a complete collection of his own plays. Shakespeare then publishes these works, which become the very same plays the time traveler originally knew. But here's the twist: where did these plays truly come from? They have no original creator. They exist in an endless loop with no clear beginning. This is the essence of the Bootstrap Paradox, where an object or piece of information is sent back in time, creating a cycle that defies our understanding of cause and effect. Unlike the grandfather paradox, which deals with altering the past, the Bootstrap Paradox challenges the very idea of origin. How can something exist without ever being created? This paradox forces us to rethink the linear nature of time and the fundamental principles of causality. It suggests that the universe might allow for events or objects to exist without a clear starting point, raising profound questions about the nature of reality itself. Examples like this have been explored in science fiction, such as in the movie Predestination, where characters grapple with the implications of self-created timelines. The Bootstrap Paradox doesn't just bend our minds, it stretches the boundaries of what we consider possible, inviting us to question the very fabric of existence. As we continue, this paradox sets the stage for even more perplexing mysteries that lie ahead in our exploration of spacetime. Now, turning to the third of our 25 spacetime paradoxes, we encounter the fascinating twin paradox. Imagine two identical twins. One stays on Earth while the other embarks on a journey through space at speeds close to the speed of light. According to Einstein's theory of relativity, time doesn't flow at the same rate for both twins. The twin traveling at near light speed experiences time more slowly compared to the twin who remains on Earth. When the spacefaring twin returns, they find that they have aged significantly less than their Earth-bound sibling. This phenomenon, known as time dilation, is a direct consequence of the laws of physics as described by relativity. the faster you move through space, the slower you move through time. This paradox isn't just a thought experiment, it has real-world implications. For instance, astronauts aboard the International Space Station experience time slightly slower than people on Earth, though the difference is minimal due to their relatively low speeds. However, for future space travelers venturing to distant stars at near-light speeds, the effects could be dramatic. The twin paradox challenges our everyday understanding of time as a constant, universal flow. Instead, it reveals that time is relative, shaped by motion and gravity. This paradox not only deepens our appreciation of Einstein's groundbreaking work, but also opens the door to possibilities for interstellar travel, where time dilation could play a crucial role. As we continue our journey through space-time, the twin paradox reminds us that the universe is far stranger and more wondrous than it appears. Now turning to the fourth of our 25 spacetime paradoxes, we delve into the Fermi Paradox, a question that has puzzled scientists and thinkers for decades. If the universe is so vast with billions of stars and planets, why haven't we found any evidence of extraterrestrial life? This contradiction lies at the heart of the Fermi Paradox. Named after physicist Enrico Fermi, who famously asked, "Where is everybody?" This paradox highlights the tension between the high probability of life existing elsewhere in the cosmos and the complete lack of observable signs of it. One of the leading explanations for this mystery is the concept of the Great Filter. This theory suggests that there may be some critical barrier, a filter, that prevents life from advancing to the point of interstellar communication or travel. The Great Filter could exist in the past, meaning that the emergence of intelligent life is extraordinarily rare, or it could lie ahead of us, posing a potential existential threat to civilizations before they can expand beyond their home planets. If the filter is behind us, it might explain why we haven't encountered other civilizations. But if it's ahead, it raises sobering questions about humanity's future. Another intriguing possibility is that advanced civilizations are intentionally avoiding detection. Perhaps they have developed technologies that make them invisible to our current methods of observation, or they might be deliberately hiding to avoid interference with less advanced species like us. This idea, sometimes called the zoo hypothesis, suggests that we might be living in a kind of cosmic preserve, observed but not contacted. The Fermi Paradox challenges us to rethink our assumptions about life, intelligence, and the nature of the universe. It forces us to confront the possibility that we might be alone, or that we might not be ready to meet our cosmic neighbors. As we continue to explore the mysteries of space-time, the Fermi Paradox reminds us that the search for extraterrestrial life is not just about finding aliens, it's about understanding our place in the cosmos. Now turning to the fifth of our 25 spacetime paradoxes, we encounter the black hole information paradox, a puzzle that strikes at the very heart of our understanding of physics. At its core, this paradox revolves around a fundamental question: what happens to information when it falls into a black hole? According to the laws of quantum mechanics, information cannot be destroyed. It must always be preserved in some form. Yet, black holes seem to defy this principle, creating a contradiction that has baffled scientists for decades. The paradox begins with the nature of black holes themselves. These cosmic phenomena are regions of spacetime where gravity is so intense that nothing, not even light, can escape. When matter or energy falls into a black hole, it appears to vanish from the universe, taking all its information with it. This poses a problem because quantum mechanics insists that information about the state of a system must always be conserved. If information is lost, it would mean that the universe is fundamentally unpredictable, undermining the very foundation of physics. Enter Stephen Hawking, whose groundbreaking work on black holes introduced the concept of Hawking radiation. Hawking proposed that black holes are not entirely black, they emit tiny amounts of radiation over time, causing them to slowly lose mass and eventually evaporate. This discovery was revolutionary, but it also deepened the paradox. If a black hole evaporates completely, what happens to the information it once contained? Does it disappear forever, or is it somehow encoded in the Hawking radiation? This question has sparked intense debate among physicists. Some argue that the information is irretrievably lost, while others believe it is preserved in subtle ways, perhaps through quantum entanglement or hidden within the fabric of spacetime itself. The debate remains unresolved, but it has led to fascinating theories, such as the idea of a firewall at the event horizon of a black hole, which could destroy information as it enters, or the holographic principle, which suggests that all the information falling into a black hole is encoded on its surface. The black hole information paradox challenges our understanding of the universe at the deepest level. It forces us to confront the limits of our knowledge and the possibility that our current theories of physics may be incomplete. As we continue to explore the mysteries of black holes, this paradox reminds us that the cosmos is full of surprises waiting to be uncovered. With the next phase of our journey in sight, we move forward to unravel yet another enigma of spacetime. Now turning to the sixth of our 25 spacetime paradoxes, we encounter one of the most famous and mind-bending thought experiments in quantum mechanics, Schrödinger's cat. This paradox, devised by physicist Erwin Schrödinger in the 1930s, challenges our understanding of reality at its most fundamental level. At its core, the paradox presents a scenario where a cat inside a sealed box is simultaneously alive and dead until the box is opened and observed. This bizarre idea stems from the principles of quantum superposition, where particles can exist in multiple states at once until they are measured. To understand this better, let's break it down. In the quantum world, particles like electrons can exist in a state of superposition, meaning they can be in multiple positions or states simultaneously. Schrödinger extended this idea to a macroscopic scale by imagining a cat placed in a box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the Geiger counter triggers the release of the poison, killing the cat. But until the box is opened and the atom is observed, it exists in a superposition of both decayed and not decayed states. As a result, the cat is both alive and dead at the same time. This thought experiment highlights the strange and counterintuitive nature of quantum mechanics. It forces us to grapple with the idea that reality is not fixed until it is observed. The act of observation or measurement collapses the superposition into a single state. This is known as the observer effect, and it raises profound questions about the role of consciousness in shaping reality. Does the universe only become definite when we look at it? Or is there something deeper at play? Schrödinger's cat also underscores the limitations of applying quantum principles to everyday objects. While superposition works for particles, extending it to larger systems like a cat leads to absurd conclusions. This paradox has sparked decades of debate and has been a cornerstone in discussions about the interpretation of quantum mechanics. Some theories, like the Copenhagen interpretation, suggest that the act of observation is what defines reality. Others, like the many worlds interpretation, propose that every possible outcome exists in parallel universes, meaning the cat is both alive in one universe and dead in another. The implications of Schrödinger's cat go far beyond a simple thought experiment. It challenges our understanding of existence, observation, and the very nature of reality. As we continue to explore the mysteries of quantum mechanics, this paradox reminds us that the universe is far stranger than we can imagine. With the next phase of our journey in sight, we move forward to unravel yet another enigma of spacetime. Now turning to the seventh of our 25 spacetime paradoxes, we delve into the Einstein-Podolsky-Rosen paradox, often referred to as the EPR paradox. This fascinating concept, introduced by Albert Einstein, Boris Podolsky, and Nathan Rosen in the 1930s, challenges the very foundations of classical physics and introduces us to the strange phenomenon of quantum entanglement. At its core, the Fermi paradox revolves around the idea that two particles can become entangled, meaning their properties are linked in such a way that the state of one particle instantly influences the state of the other, no matter how far apart they are. This instantaneous connection seems to defy the speed of light, a cornerstone of Einstein's theory of relativity, which states that nothing can travel faster than light. Einstein himself famously called this spooky action at a distance, as it appeared to violate the principles of locality and causality. To understand this better, imagine two entangled particles like electrons created together and then separated by vast distances. If you measure the spin of one electron and find it to be up, the other electron's spin will instantly be down, even if it's on the other side of the universe. This connection happens faster than light, suggesting that information is somehow being transmitted instantaneously between the particles. But how is this possible? The Fermi paradox was initially proposed as a critique of quantum mechanics, with Einstein and his colleagues arguing that the theory must be incomplete. They believed there must be hidden variables, unknown factors, that determine the properties of particles before they are measured. However, decades later, experiments conducted by physicist John Bell and others showed that no hidden variables could explain the results observed in quantum entanglement. Instead, the particles truly are connected in a way that defies classical intuition. This paradox has profound implications for our understanding of reality. It suggests that the universe is fundamentally interconnected in ways that classical physics cannot explain. Quantum entanglement is not just a theoretical curiosity, it has practical applications, particularly in the field of quantum computing. In quantum computers, entangled particles can be used to perform complex calculations at speeds far beyond what classical computers can achieve. This technology has the potential to revolutionize fields like cryptography, materials science, and artificial intelligence. The Fermi paradox also raises deep philosophical questions about the nature of reality. If particles can influence each other instantaneously across vast distances, does this mean that space and time are not as absolute as we once thought? Or is there a deeper layer of reality that we have yet to uncover? As we continue to explore the mysteries of quantum mechanics, the Fermi paradox reminds us that the universe is far more interconnected and mysterious than we can imagine. With the next phase of our journey in sight, we move forward to unravel yet another enigma of spacetime. Now turning to the 8th of our 25 spacetime paradoxes, we explore Olbers' paradox, a question that has puzzled astronomers for centuries. Why is the night sky dark? If the universe is infinite and filled with an infinite number of stars, shouldn't every point in the sky be as bright as the surface of a star? This paradox, named after the German astronomer Heinrich Olbers, challenges our understanding of the cosmos and leads us to some profound insights about the nature of the universe. At first glance, the idea seems straightforward. In an infinite universe with an infinite number of stars, every line of sight should eventually land on a star, making the night sky as bright as day. Yet, when we look up, the sky is dark, dotted only with the faint glow of distant stars and galaxies. So, what's going on? One key solution to Olbers' paradox lies in the expansion of the universe. As the universe expands, the light from distant stars and galaxies is stretched into longer, redder wavelengths, a phenomenon known as redshift. This stretching reduces the energy of the light, making it dimmer and less visible to our eyes. In essence, the light from the most distant stars never reaches us in its original form, contributing to the darkness of the night sky. Another crucial factor is the finite age of the universe. The universe is approximately 13.8 billion years old, which means light from stars beyond a certain distance hasn't had enough time to reach us yet. This creates a cosmic horizon beyond which we cannot see. If the universe were infinitely old, light from every star would have had time to travel to us, but because it's not, vast regions of the universe remain hidden in darkness. Additionally, the universe is not static. Stars are born, burn for billions of years, and eventually die. This cycle means that not all stars are shining at the same time. Some have already exhausted their fuel and faded away, while others are yet to ignite. This dynamic nature of stars further contributes to the darkness we observe. Multiverse Paradox not only highlights the limitations of our observations, but also underscores the importance of understanding the universe's history and structure. It reminds us that the cosmos is not just a static backdrop, but a dynamic, evolving entity. As we continue to probe the mysteries of the universe, this paradox serves as a reminder that even the simplest questions can lead to profound discoveries. With the next phase of our journey in sight, we move forward to unravel yet another enigma of spacetime. Now turning to the 9th of our 25 spacetime paradoxes, we delve into the Boltzmann brain paradox, a thought experiment that challenges our understanding of the universe and the nature of consciousness itself. Imagine a universe filled with chaos and randomness. In such a universe, could a fully formed, self-aware brain spontaneously emerge from the void, complete with memories and a sense of existence? This bizarre idea, proposed by the physicist Ludwig Boltzmann, raises profound questions about the nature of reality and our place within it. At its core, the Boltzmann brain paradox stems from the concept of entropy, a measure of disorder in the universe. According to the second law of thermodynamics, entropy tends to increase over time, leading to a more disordered state. However, in a universe that exists for an infinitely long time, random fluctuations could occasionally create pockets of order, even something as complex as a conscious brain. This brain would believe it exists in a structured universe, complete with memories and experiences, even though it formed entirely by chance. But why is this idea so unsettling? If such a brain could spontaneously form, it raises the possibility that our own consciousness might be the result of a random fluctuation rather than a product of a real, structured universe. In other words, we might be Boltzmann brains, imagining the world around us rather than truly experiencing it. This paradox forces us to confront the reliability of our perceptions and the very foundations of what we consider to be real. The implications of the Boltzmann brain paradox extend far beyond philosophy. In cosmology, it challenges our understanding of the universe's origins and its ultimate fate. If the universe is infinite and eternal, the probability of such random fluctuations increases, making the existence of Boltzmann brains more likely. This idea has led scientists to question whether our current models of the universe are incomplete, or if there's a deeper principle at work that prevents such anomalies. Moreover, the paradox touches on the nature of consciousness itself. If a Boltzmann brain can exist, what does that say about the relationship between the mind and the physical world? Are our thoughts and experiences merely the result of random chance, or is there something more fundamental at play? These questions push the boundaries of both physics and philosophy, inviting us to rethink our assumptions about reality. As we grapple with the Boltzmann brain paradox, we're reminded that the universe is full of mysteries that defy easy explanations. This paradox not only challenges our understanding of cosmology, but also invites us to reflect on the nature of existence and consciousness. With the next phase of our journey in sight, we move forward to explore yet another enigma of spacetime, where the boundaries of science and imagination continue to blur. Now turning to the 10th of our 25 spacetime paradoxes, we explore the simulation paradox, a concept that challenges the very nature of our reality. What if everything we perceive, our world, our experiences, even our consciousness, is nothing more than an elaborate simulation? This idea, once confined to the realms of science fiction, has gained traction among philosophers, scientists, and technologists, sparking debates about the nature of existence and the limits of human understanding. At its heart, the simulation paradox stems from the rapid advancements in technology, particularly in computing and artificial intelligence. If we continue to develop increasingly sophisticated simulations, it's conceivable that future civilizations could create virtual worlds indistinguishable from reality. But here's the twist: if such simulations are possible, how can we be certain that we're not already living in one? This question, famously posed by philosopher Nick Bostrom, forms the basis of the simulation argument, which suggests that one of three possibilities must be true. Either advanced civilizations never reach the capability to create such simulations, they choose not to create them, or we are almost certainly living in one. The implications of this paradox are profound. If our reality is a simulation, it raises questions about the nature of free will, the purpose of existence, and the role of the programmers who designed our world. Are we merely characters in a cosmic video game following predetermined scripts, or do we have the autonomy to shape our own destinies? These questions blur the lines between science and philosophy, challenging us to rethink our understanding of reality. From a technological standpoint, the simulation paradox also highlights the ethical dilemmas of creating simulated worlds. If we were to develop such simulations, would the beings within them possess consciousness? If so, what responsibilities would we have toward them? These questions touch on the moral implications of playing the role of creators, forcing us to confront the potential consequences of our technological ambitions. As we grapple with the simulation paradox, we're reminded that the boundaries between reality and illusion may be far more fluid than we once believed. This paradox not only challenges our understanding of the universe, but also invites us to reflect on the nature of existence and our place within it. With the next phase of our journey in sight, we move forward to explore yet another enigma of space-time, where the mysteries of the cosmos continue to unfold. Now turning to the 11th of our 25 spacetime paradoxes, we delve into the arrow of time paradox, a concept that probes the one-way flow of time in a universe governed by laws that seem indifferent to its direction. At first glance, the laws of physics appear to be time-symmetric, meaning they work the same whether time moves forward or backward. Yet, our everyday experience tells us that time only moves in one direction forward. So, why does time have an arrow? The answer lies in the concept of entropy, a measure of disorder in a system. The second law of thermodynamics states that in an isolated system, entropy always increases over time. This increase in entropy gives time its direction, creating what we perceive as the arrow of time. Imagine a shattered glass. It's easy to break, but nearly impossible for the pieces to spontaneously reassemble into a whole. This irreversible process is a direct consequence of increasing entropy. The Big Bang also plays a crucial role in shaping the arrow of time. At the moment of the Big Bang, the universe began in a state of extremely low entropy, setting the stage for the relentless march toward higher entropy that defines the flow of time. Without this initial low entropy state, the arrow of time as we know it wouldn't exist. This raises an intriguing question. Why did the universe start in such a low entropy state? Some scientists suggest it might be a result of the fundamental laws of physics, while others propose it could be a feature of the multiverse, where our universe is just one of many with varying initial conditions. Beyond the physical explanations, the arrow of time also has a psychological dimension. Our perception of time is deeply tied to memory and anticipation. We remember the past but not the future, and we feel as though we're constantly moving toward what's next. This psychological arrow of time aligns with the thermodynamic arrow, creating a coherent experience of time's flow. Yet, this raises another paradox. If the laws of physics are time-symmetric, why do we perceive time as moving forward? Some theories suggest that consciousness itself might be linked to the increase of entropy, though this remains a topic of debate. The arrow of time paradox challenges us to reconcile the symmetry of physical laws with the asymmetry of our experience. It invites us to explore the deep connections between the cosmos, entropy, and the nature of consciousness. As we continue our journey through the mysteries of space-time, we move forward to uncover yet another paradox that pushes the boundaries of our understanding. Now turning to the 12th of our 25 spacetime paradoxes, we encounter the quantum Zeno paradox, a fascinating phenomenon that reveals how the act of observation can freeze a quantum system in place. Named after the ancient Greek philosopher Zeno of Elea, who proposed that motion is an illusion, this paradox challenges our understanding of how quantum systems evolve over time. At its core, the quantum Zeno paradox suggests that if you observe a quantum system frequently enough, you can effectively prevent it from changing. This might sound counterintuitive, but it stems from the peculiar nature of quantum mechanics. In the quantum world, particles exist in a superposition of states, meaning they can be in multiple states at once until they are observed. When an observation is made, the system collapses into one of its possible states. If you keep observing the system repeatedly, it doesn't have time to evolve, effectively locking it in its initial state. To put it simply, imagine flipping a coin. In the quantum realm, the coin is both heads and tails until you look at it. If you keep checking the coin over and over again, it never gets the chance to land on one side. It stays in that ambiguous state. This effect, known as the quantum Zeno effect, has been experimentally verified in laboratories, showing that continuous observation can indeed halt the natural evolution of quantum systems. The implications of this paradox are profound. It challenges the idea that observation is a passive act, revealing instead that the observer plays an active role in shaping reality. This has led to debates about the nature of measurement in quantum mechanics and the role of consciousness in the physical world. Some scientists even speculate that the quantum Zeno effect could be harnessed for practical applications, such as stabilizing quantum computers or protecting fragile quantum states from decoherence. In the realm of technology, the quantum Zeno effect could revolutionize how we approach quantum computing. By preventing unwanted changes in quantum states, we might be able to create more stable and reliable quantum systems, paving the way for breakthroughs in computing power and data security. However, this also raises ethical questions about the limits of control and the potential consequences of manipulating quantum systems. The quantum Zeno paradox not only deepens our understanding of quantum mechanics, but also blurs the line between observer and observed. As we continue to explore the mysteries of space-time, this paradox reminds us that the act of looking can sometimes change what we see, or even stop it from changing altogether. With this in mind, we move forward to uncover yet another paradox that challenges our perception of reality. Now turning to the 13th of our 25 spacetime paradoxes, we delve into the unravel effect paradox, a mind-bending concept that reveals how motion can alter our perception of reality. At its heart, this paradox explores the idea that an accelerating observer perceives a vacuum not as empty, but as filled with particles. This startling phenomenon challenges our understanding of what constitutes nothingness, and forces us to reconsider the very nature of reality. The unravel effect, named after physicist William Unruh, arises from the principles of quantum field theory. According to this theory, even in a vacuum, a space devoid of matter, there are fluctuations of energy known as quantum fields. For an observer at rest or moving at a constant speed, these fluctuations remain invisible and the vacuum appears empty. However, for an observer accelerating through space, these quantum fields manifest as a sea of particles, creating what is known as unravel radiation. In other words, the act of acceleration transforms the vacuum into a thermal bath of particles, with the temperature of this radiation directly proportional to the observer's acceleration. To put it simply, imagine floating in a completely dark room. If you stay still, the room feels empty, but if you start moving rapidly, you suddenly sense warmth and light, as if the room is filled with glowing particles. This is analogous to what an accelerating observer experiences in a vacuum. A seemingly empty space becomes alive with energy. The unravel effect has profound implications, particularly in its connection to Hawking radiation, the phenomenon where black holes emit radiation due to quantum effects near their event horizons. Both effects stem from the idea that different observers can perceive the same quantum field in radically different ways. While Hawking radiation arises from the intense gravitational field of a black hole, the unravel effect is driven by acceleration. Together, they highlight the deep interplay between motion, gravity, and quantum mechanics. This paradox also raises questions about the nature of reality itself. If what one observer perceives as empty space appears as a particle-filled environment to another, whose perspective is real, the unravel effect suggests that reality is not absolute but depends on the observer's state of motion. This challenges the classical notion of an objective, observer-independent universe and aligns more closely with the principles of relativity and quantum mechanics. In the realm of theoretical physics, the unravel effect continues to inspire research into the fundamental nature of spacetime and quantum fields. It also serves as a reminder that our understanding of the universe is deeply tied to how we observe and interact with it. As we explore this paradox, we are reminded that even the vacuum of space is far from empty. It is a dynamic, observer-dependent tapestry of energy and particles. With this in mind, we move forward to uncover yet another paradox that challenges our perception of reality, bringing us closer to unraveling the mysteries of spacetime. Now turning to the 14th of our 25 spacetime paradoxes, we encounter the Banach-Tarski paradox, a mathematical enigma that defies our intuitive understanding of space and volume. This paradox, named after mathematicians Stefan Banach and Alfred Tarski, reveals a startling possibility. A solid object, such as a sphere, can be divided into a finite number of pieces and then reassembled into two identical copies of the original object. At first glance, this seems impossible. How can one object become two without adding any new material? Yet, this paradox emerges from the strange and counterintuitive world of infinite sets and non-measurable spaces. The Banach-Tarski paradox relies on the concept of infinity and the peculiar properties of certain mathematical constructions. In essence, the paradox exploits the fact that in infinite sets, it is possible to create subsets that are as large as the original set itself. By carefully dividing the object into these subsets and rearranging them, mathematicians can effectively double the object without violating the rules of geometry. However, this process only works because the pieces involved are so intricately fragmented that they cannot be assigned a traditional volume or size. These pieces are said to be non-measurable, meaning they exist in a realm beyond our everyday experience of space and matter. To grasp this idea, imagine a loaf of bread. In the real world, if you cut the loaf into pieces and rearrange them, you can never end up with two identical loaves of the same size. But in the abstract world of the Banach-Tarski paradox, the loaf can be sliced into infinitely complex shapes that, when reassembled, create two perfect copies. This paradox challenges our understanding of physical reality, suggesting that space itself may have properties that are far more bizarre than we can perceive. The implications of the Banach-Tarski paradox extend beyond pure mathematics. It raises profound questions about the nature of space, infinity, and the limits of human intuition. If space can be manipulated in such a way that one object becomes two, what does this say about the fabric of the universe? Could there be regions of space where the rules of volume and size break down, allowing for such paradoxical phenomena? While the paradox does not directly apply to the physical world as we know it, it serves as a reminder that our understanding of reality is limited by the tools and frameworks we use to describe it. In the realm of theoretical physics, the Banach-Tarski paradox has inspired discussions about the nature of spacetime and the possibility of hidden dimensions or structures that defy conventional geometry. It also highlights the importance of mathematical rigor in exploring the boundaries of our knowledge. As we ponder this paradox, we are reminded that the universe is full of mysteries that challenge our most fundamental assumptions. With this in mind, we move forward to explore yet another paradox that pushes the boundaries of our understanding, bringing us closer to unraveling the secrets of spacetime. Now turning to the 15th of our 25 spacetime paradoxes, we delve into the dark matter paradox, a mystery that lies at the heart of modern cosmology. Dark matter is an invisible substance that makes up approximately 85% of the universe's total mass, yet it remains undetectable through conventional means. This paradox challenges our understanding of the cosmos, as we can observe its gravitational effects on galaxies and galaxy clusters, but we cannot see or directly measure it. The existence of dark matter was first proposed to explain the unusual behavior of galaxies. Observations showed that stars on the outer edges of galaxies were moving faster than expected, suggesting the presence of additional mass that was not visible. This unseen mass, now known as dark matter, exerts a gravitational pull that holds galaxies together and shapes the large-scale structure of the universe. Despite its pervasive influence, dark matter does not interact with light or other forms of electromagnetic radiation, making it invisible to telescopes and other instruments designed to detect light. Scientists have proposed several theories to explain the nature of dark matter. One leading hypothesis suggests that dark matter is composed of weakly interacting massive particles, or WIMP. These hypothetical particles would interact only through gravity and the weak nuclear force, making them extremely difficult to detect. Another theory posits that dark matter could be made up of actions, extremely light particles that could permeate the universe without interacting with ordinary matter. However, despite decades of research, no direct evidence of these particles has been found. Ongoing experiments aim to uncover the secrets of dark matter. Deep underground laboratories, shielded from cosmic radiation, house detectors designed to capture rare interactions between dark matter particles and ordinary matter. Space-based observatories, such as the European Space Agency's Euclid mission, are mapping the distribution of dark matter across the universe by studying its gravitational effects on light from distant galaxies. These efforts represent humanity's quest to solve one of the greatest mysteries in science. The dark matter paradox not only challenges our understanding of the universe, but also raises profound questions about the nature of reality. If dark matter is so abundant yet so elusive, what does this say about the limits of our observational tools and theoretical frameworks? Could there be entirely new forms of matter or forces at play that we have yet to discover? As we continue to explore this paradox, we are reminded that the universe is far more complex and mysterious than we can currently comprehend. With this in mind, we move forward to explore yet another paradox that pushes the boundaries of our understanding, bringing us closer to unraveling the secrets of spacetime. Now turning to the 16th of our 25 spacetime paradoxes, we encounter the dark energy paradox, a phenomenon that has left scientists both fascinated and perplexed. Dark energy is the mysterious force responsible for the accelerating expansion of the universe, yet its true nature remains one of the greatest unsolved mysteries in modern cosmology. Unlike dark matter, which exerts a gravitational pull, dark energy appears to act as a repulsive force, pushing galaxies apart at an ever-increasing rate. The discovery of dark energy came as a shock to the scientific community in the late 1990s. Observations of distant supernova revealed that the universe was not only expanding but doing so at an accelerating pace. This finding contradicted the prevailing belief that the expansion should be slowing down due to the gravitational attraction of matter. To explain this unexpected behavior, scientists proposed the existence of dark energy, a form of energy that permeates all of space and drives the acceleration. One of the leading theories about dark energy is that it is a property of space itself, often referred to as the cosmological constant. This idea, first introduced by Albert Einstein, suggests that empty space is not truly empty but contains a constant energy density that exerts a repulsive force. However, the observed value of this energy density is incredibly small, raising questions about why it is so finely tuned. Another possibility is that dark energy is a dynamic field, similar to the Higgs field, which changes over time and could eventually alter the fate of the universe. The dark energy paradox poses significant challenges to our understanding of physics. If dark energy continues to dominate, the universe could expand indefinitely, leading to a cold and desolate future known as the Big Freeze. Alternatively, if dark energy evolves in unexpected ways, it could trigger a big rip, tearing apart galaxies, stars, and even atoms. These scenarios highlight the profound implications of dark energy for the ultimate fate of the cosmos. Efforts to unravel the mystery of dark energy are ongoing. Projects like the Dark Energy Survey and the upcoming Vera-C Rubin Observatory aim to map the distribution of galaxies and measure the rate of cosmic expansion with unprecedented precision. These observations could provide clues about the nature of dark energy and its role in shaping the universe. Yet, despite these advancements, dark energy remains an enigma, reminding us that the cosmos is full of surprises. As we grapple with the dark energy paradox, we are confronted with fundamental questions about the nature of reality. What is the source of this mysterious force? How does it fit into our current understanding of physics? And what does its existence tell us about the ultimate destiny of the universe? These questions drive us to explore deeper, pushing the boundaries of human knowledge and inspiring new discoveries. With this paradox in mind, we now turn to the next chapter of our journey, where another space-time mystery awaits to challenge our understanding of the cosmos. Now turning to the 17th of our 25 space-time paradoxes, we delve into the Multiverse Paradox, a concept that stretches the boundaries of our imagination. The idea of multiple universes coexisting alongside our own has long fascinated scientists, philosophers, and storytellers alike. But what if these parallel worlds are not just the stuff of science fiction? What if they are real and our universe is just one of countless others in an infinite cosmic tapestry? The multiverse paradox arises from theories in quantum mechanics and cosmology that suggest the existence of multiple universes, each with its own unique set of physical laws and constants. One of the most well-known frameworks for this idea is the many worlds interpretation of quantum mechanics. According to this theory, every time a quantum event occurs, such as the decay of a radioactive atom or the spin of an electron, the universe splits into multiple branches, creating a new reality for every possible outcome. In this view, every decision you make, no matter how small, spawns an alternate universe where a different version of you exists. But the many worlds interpretation is just one piece of the multiverse puzzle. Cosmologists have proposed other models, such as the inflationary multiverse, which suggests that our universe is just one bubble in a vast cosmic foam of universes, each born from a different region of space during the rapid expansion of the early universe. Another intriguing idea is the brain multiverse, rooted in string theory, which posits that our universe exists on a three-dimensional brain, floating in a higher dimensional space, alongside countless other brains that could each house their own universe. While these theories are captivating, they also present significant challenges. How do we prove or disprove the existence of other universes if they are, by definition, beyond our observational reach? Some scientists argue that evidence for the multiverse could be found in the cosmic microwave background radiation, the faint afterglow of the Big Bang. Others suggest that gravitational waves or anomalies in the distribution of matter in our universe might provide clues. Yet, these ideas remain speculative, and the multiverse paradox continues to spark debate among physicists. The implications of the multiverse are profound. If an infinite number of universes exist, does that mean every possible outcome of every event has already occurred somewhere? Does it render our choices meaningless, or does it open up new possibilities for understanding our place in the cosmos? These questions challenge not only our scientific understanding but also our philosophical and existential perspectives. As we explore the multiverse paradox, we are reminded that the universe, or perhaps the multiverse, is far stranger and more complex than we can imagine. The search for answers drives us to push the limits of human knowledge, inspiring new theories, experiments, and ways of thinking. And with this paradox in mind, we now turn to the next chapter of our journey, where another space-time mystery awaits to challenge our understanding of the cosmos. Now turning to the 18th of our 25 space-time paradoxes, we encounter the time traveler's dilemma, a thought experiment that forces us to confront the ethical and logical complexities of time travel. Imagine for a moment that you could journey back in time. What would you change? Would you prevent a tragedy, correct a mistake, or perhaps even alter the course of history itself? While this idea has fueled countless science fiction stories, it also raises profound questions about causality, responsibility, and the very nature of reality. At the heart of the time traveler's dilemma is the question of whether altering the past is even possible, and if so, what the consequences might be. One of the most famous examples of this paradox comes from science fiction, the grandfather paradox. If you were to travel back in time and prevent your own grandfather from meeting your grandmother, you would effectively erase your own existence. But if you never existed, how could you have traveled back in time to make that change in the first place? This creates a logical loop that seems impossible to resolve. Theoretical physics offers some intriguing possibilities for navigating this paradox. One idea is the concept of self-consistent timelines, where any changes made in the past are already part of the history you remember. In this view, your actions in the past would align with the events that led to your present, avoiding contradictions. Another theory suggests that time travel could create alternate timelines or parallel universes, where your actions in the past spawn a new reality separate from your original timeline. This idea, often explored in science fiction, provides a way to sidestep the grandfather paradox but raises new questions about the nature of identity and the consequences of our choices. Beyond the logical challenges, the time traveler's dilemma also forces us to grapple with ethical questions. If you could change the past, should you? What if your actions had unintended consequences, leading to outcomes far worse than the original timeline? For example, preventing a historical tragedy might seem like an obvious good, but what if that event was a catalyst for positive change in the long run? These dilemmas highlight the complexity of human history and the interconnectedness of events, reminding us that even the smallest actions can have far-reaching effects. The time traveler's dilemma also touches on the nature of free will and determinism. If the past can be changed, does that mean the future is not fixed? Or are our actions in the past and the present predetermined by the laws of physics? These questions challenge our understanding of time, causality, and the very fabric of reality, pushing the boundaries of both science and philosophy. As we ponder the time traveler's dilemma, we are reminded that time travel, if it were possible, would not be a simple matter of revisiting the past or glimpsing the future. It would force us to confront profound questions about who we are, the choices we make, and the consequences of those choices. And with this paradox in mind, we now turn to the next chapter of our journey, where another space-time mystery awaits to challenge our understanding of the cosmos. Now turning to the 19th of our 25 space-time paradoxes, we delve into the quantum suicide paradox, a thought experiment that takes the concept of parallel universes to a chilling extreme. Imagine a scenario where a person is placed in a device that triggers a quantum event, something like the flip of a quantum coin, that has a 50% chance of either killing them or leaving them unharmed. According to the principles of quantum mechanics, every possible outcome of this event exists in a separate universe. In one universe, the person dies. In another, they survive, but here's where it gets mind-bending. From the perspective of the person undergoing the experiment, they can only ever experience the universes where they survive. This leads to the startling idea that, in a sense, the person could achieve a form of immortality. No matter how many times the experiment is repeated, the person will always find themselves in a universe where they continue to live. This paradox raises profound questions about the nature of reality and consciousness. Are we, in some way, always the survivors of our own quantum experiments? And if so, what does that mean for our understanding of life, death, and the multiverse? The quantum suicide paradox also challenges our notions of probability and observation. In the many worlds interpretation of quantum mechanics, every possible outcome of a quantum event branches off into its own universe. This means that, in theory, there are countless versions of reality where different outcomes play out. But from our perspective, we only ever experience one of those realities. This leads to the unsettling idea that our perception of reality is inherently biased. We only see the outcomes that align with our continued existence. Philosophically, this paradox forces us to confront the nature of identity and continuity. If there are infinite versions of ourselves in parallel universes, which one is the real us? And if we can only ever experience the universes where we survive, does that mean our consciousness is somehow tied to those specific realities? These questions blur the line between science and philosophy, challenging us to rethink what it means to exist in a multiverse. As we grapple with the quantum suicide paradox, we are reminded of the strange and often counterintuitive nature of quantum mechanics. It's a realm where the rules of classical physics no longer apply, and where the very act of observation can shape reality. And with this paradox in mind, we now turn to the next chapter of our journey, where another spacetime mystery awaits to challenge our understanding of the cosmos. Now turning to the 20th of our 25 spacetime paradoxes, we explore the observer effect paradox, a phenomenon that lies at the heart of quantum mechanics. At its core, this paradox reveals that the mere act of observing a quantum system can fundamentally change its behavior. Imagine a particle, like an electron, existing in a state of superposition, meaning it can be in multiple states or locations simultaneously. However, the moment we attempt to measure or observe it, the particle chooses a single state or location. This raises a profound question. Does the act of observation itself force the particle to collapse into a definite state, or is there something deeper at play? The observer effect paradox challenges our classical understanding of reality. In the everyday world, we assume that objects exist independently of whether we're looking at them or not. But in the quantum realm, this assumption breaks down. The behavior of particles seems to depend on whether they are being observed, suggesting that consciousness, or at least the act of measurement, plays a crucial role in shaping reality. This idea has sparked intense debate among physicists and philosophers alike. Is reality something that exists objectively, or is it, in some way, created or influenced by our observations? One of the most famous experiments illustrating this paradox is the double-slit experiment. When particles like electrons are fired at a barrier with two slits, they create an interference pattern on the other side, as if they were waves. But when scientists place detectors to observe which slit the particles pass through, the interference pattern disappears and the particles behave like discrete objects. This suggests that the act of observation changes the very nature of the particles, forcing them to decide how to behave. The implications of the observer effect paradox extend far beyond the laboratory. If observation can influence the behavior of particles, what does that mean for our understanding of the universe? Some interpretations suggest that consciousness itself might be a fundamental aspect of reality, shaping the world around us in ways we don't yet fully understand. Others argue that the effect is purely a result of the interaction between the measuring device and the quantum system, with no need to invoke consciousness. Regardless of the interpretation, this paradox forces us to reconsider the relationship between the observer and the observed. As we reflect on the observer effect paradox, we are reminded of the strange and interconnected nature of the quantum world. It's a realm where the boundaries between observer and observed blur, and where the very act of looking can change what we see. And with this paradox in mind, we now turn to the next chapter of our journey, where another space-time mystery awaits to challenge our understanding of the cosmos. Now turning to the 21st of our 25 space-time paradoxes, we delve into the heat-death paradox, a concept that paints a chilling picture of the universe's ultimate fate. At its core, this paradox revolves around the idea of entropy, the measure of disorder in a system. Over time, the universe tends toward maximum entropy, a state where all energy is evenly distributed, and no usable energy remains to sustain motion, life, or even the passage of time. This scenario, often referred to as the heat death of the universe, suggests a future where the cosmos becomes a cold, dark, and lifeless expanse. The heat death paradox challenges our understanding of time and existence. In this state, all stars will have burned out, all matter will have decayed, and all processes that rely on energy gradients like life itself will cease to function. The universe will reach a state of thermodynamic equilibrium where nothing changes and nothing happens. It's a stark contrast to the dynamic, ever-evolving cosmos we see today. But what does this mean for the concept of time? If time is defined by change, what happens when change itself comes to an end? This paradox also raises profound questions about the nature of life and its place in the universe. If the ultimate fate of the cosmos is heat-death, does that render life meaningless, or does it underscore the preciousness of the fleeting moments we have? Some scientists and philosophers argue that the inevitability of heat-death should inspire us to cherish the present and strive to make the most of our time in the universe. Others see it as a call to explore ways to extend life and civilization beyond the limits imposed by entropy, perhaps by harnessing the energy of black holes or finding ways to escape to other universes. The heat-death paradox also ties into broader questions about the nature of the cosmos. Is heat-death truly inevitable, or could there be mechanisms perhaps hidden in the laws of physics or the fabric of space-time that could prevent it? Some theories suggest that the universe might undergo cycles of expansion and contraction, avoiding heat-death altogether. Others propose that new forms of energy or matter could emerge, resetting the cosmic clock. While these ideas remain speculative, they remind us that our understanding of the universe is still evolving. As we contemplate the heat-death paradox, we are confronted with the fragility and impermanence of existence. It's a reminder that the universe, for all its vastness and complexity, is not eternal. And yet, within this finite framework, there is beauty, wonder, and the potential for discovery. With this paradox in mind, we now turn to the next chapter of our journey, where another space-time mystery awaits to challenge our understanding of the cosmos. Now turning to the 22nd of our 25 space-time paradoxes, we explore the singularity paradox, a concept that lies at the heart of some of the most profound mysteries in physics. Singularities are points in space where the laws of physics as we know them break down. They are found in two of the most extreme environments in the universe, the centers of black holes and the moment of the Big Bang. In these regions, gravity becomes infinitely strong, and matter is crushed to an infinitely small point, creating conditions that our current theories cannot fully explain. The singularity paradox challenges our understanding of the universe because it represents a boundary beyond which science cannot yet see. In the case of black holes, a singularity forms when a massive star collapses under its own gravity, creating a region of space-time where the gravitational pull is so intense that not even light can escape. This singularity is hidden behind the event horizon, the point of no return. But what happens inside? Our equations predict infinite density and infinite curvature of space-time, but infinities in physics are often a sign that our theories are incomplete. Similarly, the Big Bang singularity marks the beginning of our universe. According to the prevailing model, the universe started as an infinitely dense and hot point that rapidly expanded. But what caused this expansion? What existed before the Big Bang? These questions push the limits of our scientific knowledge, as our current understanding of physics cannot describe the conditions at or before the singularity. The singularity paradox also raises questions about the nature of reality itself. Are singularities real, or are they mathematical artifacts that point to the need for a deeper theory? Some scientists believe that a theory of quantum gravity, which unites general relativity and quantum mechanics, could resolve these infinities and provide a clearer picture of what happens at these extreme points. For example, string theory and loop quantum gravity propose that singularities might be replaced by finite, albeit highly exotic, structures. This paradox also invites us to consider the limits of human knowledge. Singularities remind us that there are aspects of the universe that may forever remain beyond our grasp. Yet, they also inspire us to push the boundaries of science, to develop new theories and technologies that might one day unravel these mysteries. As we grapple with the singularity paradox, we are reminded that the universe is full of wonders that challenge our imagination and drive our quest for understanding. With this paradox in mind, we now turn to the next chapter of our journey, where another space-time mystery awaits to challenge our understanding of the cosmos. Now turning to the 23rd of our 25 space-time paradoxes, we delve into the holographic principle paradox, a concept that suggests the universe might be a hologram. Imagine a world where all the information about everything in the cosmos is encoded not within the three-dimensional space we experience, but on a two-dimensional boundary surrounding it. This idea, while seemingly straight out of science fiction, has profound implications for our understanding of quantum gravity and the very nature of reality. The holographic principle was first proposed in the context of black hole physics. Scientists discovered that the amount of information a black hole can contain is proportional not to its volume, but to the area of its event horizon. This led to the radical idea that all the information about what falls into a black hole could be encoded on its surface. Extending this idea further, some physicists suggest that the entire universe might operate in a similar way, with all the information about the cosmos encoded on its boundary. This paradox challenges our conventional view of space and time. If the universe is a hologram, then the three-dimensional reality we perceive might be a projection of information stored on a two-dimensional surface. This would mean that the fabric of reality is far more interconnected and unified than we currently understand. It also raises questions about the nature of space itself. Is space fundamental, or is it an emergent property of deeper, more fundamental processes? The holographic principle has significant implications for quantum gravity, the quest to unify general relativity and quantum mechanics. If the universe is holographic, it suggests that the fundamental building blocks of reality might not be particles or fields, but bits of information. This idea aligns with theories like string theory and loop quantum gravity, which propose that space-time itself might be composed of discrete, quantized units. Moreover, this paradox invites us to reconsider the nature of reality. If the universe is a hologram, then what we perceive as solid, tangible objects might be illusions, projections of information from a deeper, more fundamental layer of existence. This idea resonates with philosophical questions about the nature of perception and reality, echoing ancient debates about the true nature of the world. As we explore the holographic principle paradox, we are reminded that the universe is full of mysteries that challenge our understanding and push the boundaries of science. This paradox not only deepens our quest for a unified theory of physics, but also invites us to ponder the very nature of existence. With this thought-provoking concept in mind, we now move forward to the next chapter of our journey, where another space-time mystery awaits to challenge our understanding of the cosmos. Now turning to the 24th of our 25 space-time paradoxes, we explore the cosmic censorship paradox, a concept that delves into the mysterious nature of singularities and their relationship with black holes. Singularities, as predicted by Einstein's theory of general relativity, are points where gravity becomes infinitely strong and the laws of physics as we know them break down. These extreme regions are thought to exist at the center of black holes, but here's the catch: they are hidden from our view, shielded by what we call the event horizon. The cosmic censorship paradox arises from the idea that singularities are always censored by event horizons, preventing them from being directly observed. This concept, proposed by physicist Roger Penrose, suggests that nature has a built-in mechanism to protect the universe from the chaotic and unpredictable effects of naked singularities, those not hidden behind an event horizon. If such singularities were exposed, they could disrupt the fabric of space-time in ways that defy our understanding of physics, leading to unpredictable and potentially catastrophic consequences. This paradox plays a crucial role in black hole physics. The event horizon acts as a boundary beyond which nothing, not even light, can escape. It effectively hides the singularity from the outside universe, maintaining a sense of order and stability. Without this cosmic censorship, the universe as we know it might not be able to function in a predictable manner. The paradox raises profound questions about the nature of space-time and the limits of our knowledge. Are singularities always hidden, or could there be exceptions where they become visible? The stability of the universe hinges on this paradox. If naked singularities were to exist, they could create regions where the laws of physics no longer apply, leading to scenarios where cause and effect break down. This would challenge our understanding of the universe's structure and the predictability of physical laws. The cosmic censorship paradox, therefore, not only deepens our understanding of black holes, but also underscores the delicate balance that keeps the cosmos stable. As we ponder this paradox, we are reminded of the intricate and often hidden mechanisms that govern the universe. The cosmic censorship paradox invites us to question the boundaries of our knowledge and the nature of reality itself. With this thought-provoking concept in mind, we now move forward to the final chapter of our journey, where one last space-time mystery awaits to challenge our understanding of the cosmos. Now turning to the 25th and final space-time paradox in our exploration, we delve into the information paradox in quantum gravity, a puzzle that lies at the heart of modern physics. This paradox highlights the fundamental conflict between two of the most successful theories in science, quantum mechanics and general relativity. While quantum mechanics governs the behavior of particles at the smallest scales, general relativity describes the force of gravity and the structure of the universe on a cosmic scale. Yet, when it comes to understanding what happens to information in extreme environments like black holes, these two theories seem to clash in profound and unresolved ways. At the core of this paradox is the question of what happens to information when matter falls into a black hole. According to quantum mechanics, information is never truly lost. It might change form, but it is always preserved. This principle is known as the conservation of information. However, general relativity predicts that when matter crosses the event horizon of a black hole, it is crushed into a singularity, a point of infinite density where the laws of physics break down. If this is true, then the information about that matter would seemingly vanish from the universe, violating the principles of quantum mechanics. This contradiction became even more puzzling with Stephen Hawking's discovery of Hawking radiation. Black holes, according to Hawking, are not entirely black. They emit radiation over time, slowly losing energy and mass until they eventually evaporate. But here's the problem. Hawking radiation appears to be random, carrying no information about the matter that fell into the black hole. If the black hole evaporates completely, what happens to the information it once contained? Does it disappear forever, or is there some way it escapes? This paradox has sparked decades of debate and inspired groundbreaking research. One proposed solution is the idea of black hole complementarity, which suggests that information is both preserved inside the black hole and encoded in the Hawking radiation outside without violating the laws of physics. Another theory, known as the holographic principle, posits that all the information about matter falling into a black hole is stored on its surface like a hologram and can eventually be retrieved. These ideas push the boundaries of our understanding, suggesting that spacetime itself might have a deeper, more fundamental structure than we currently realize. Efforts to resolve the information paradox have also led to the development of new frameworks, such as string theory and loop quantum gravity, which aim to unify quantum mechanics and general relativity into a single, coherent theory of quantum gravity. These theories attempt to describe the universe at its most fundamental level, where the rules of quantum mechanics and gravity merge into one. While progress has been made, the information paradox remains one of the most challenging and exciting problems in physics, driving scientists to rethink the very nature of reality. As we conclude our journey through these 25 spacetime paradoxes, we are left with a profound sense of wonder and curiosity. Each paradox challenges our understanding of the universe, pushing us to explore deeper and ask bigger questions. The information paradox in quantum gravity, in particular, reminds us that the cosmos is full of mysteries waiting to be unraveled. What other secrets lie hidden in the fabric of spacetime? What new discoveries await us as we continue to probe the boundaries of science? The answers, as always, lie just beyond the horizon of our current knowledge, inviting us to keep exploring, questioning, and dreaming. Now turning to the conclusion of our journey through these 25 spacetime paradoxes, we find ourselves standing at the edge of human understanding, gazing into the vast unknown. Each paradox we've explored, from the mind-bending grandfather paradox to the enigmatic information paradox in quantum gravity, has challenged our perceptions of reality, time, and the very fabric of the universe. These puzzles are not just intellectual curiosities, they are the driving force behind some of the most groundbreaking discoveries in science. They remind us that the universe is far stranger and more complex than we can imagine, and that every answer we uncover only leads to more questions. These paradoxes push the boundaries of human knowledge, forcing us to rethink the laws of physics, the nature of time, and the limits of our understanding. They inspire us to dream bigger, to explore deeper, and to never stop questioning. Whether it's the mystery of dark matter, the riddle of black holes, or the possibility of parallel universes, each paradox invites us to venture into uncharted territory where the rules of reality as we know them may no longer apply. As we reflect on these 25 paradoxes, we're left with a profound sense of awe and curiosity. The universe is a place of infinite wonder, filled with mysteries waiting to be unraveled. What other secrets lie hidden in the cosmos? What new paradoxes will we discover as we continue to probe the depths of space and time? The journey of exploration is far from over, and the questions we ask today may shape the discoveries of tomorrow. Before we wrap up, I'd love to hear your thoughts. Which of these paradoxes fascinates you the most? Do you have your own theories about the mysteries of the universe? Share your ideas in the comments below. I'm excited to hear your perspectives. And if you enjoyed this journey through the cosmos, don't forget to subscribe and hit the notification bell so you never miss an exploration into the wonders of space and time. Together, let's keep unraveling the mysteries of the universe, one paradox at a time.